To interpret the effect that an explanatory variable has on our response for a proportional odds regression model, we use odds ratios. And so what you're going to see in this set of notes is a lot of similarities to what we did for odds ratios with respect to logistic regression because of the form of this proportional odds regression model. There are differences, of course, because now we're working with cumulative probabilities. Okay, so let's consider the model again, where we only have one explanatory variable. And what we could do is rewrite this as, in terms of the odds, okay. So once we have the odds in, we can find an odds ratio where we can compare, let's say, x where we look at the ratio with respect to a C unit increase in x. So to do that, here's the odds for a C unit increase in x. Here's the odds just at x itself. Notice the notation here. I put in parentheses the y less than or equal to j, just to emphasize that we're working with these cumulative probabilities. So here's my odds. Notice this is what goes in the numerator. What goes in the denominator is if I add c, this goes in the denominator, this goes into the numerator where I have x plus c in there instead. And so, of course, then some things cancel out like what we've seen in the past, and we're left with the exponential function evaluated at c times beta 1. So notice that x does not play a role. So to interpret then this odds ratio, we can say that the odds of a y less than or equal to j versus a y greater than j response are the exponential function evaluated at c times beta 1 times as large for a c unit increase in x. Alternatively, another valid interpretation would be the odds of a y less than or equal to j versus y greater than j changed by e to the c times beta 1 times for every c unit increase in x. Now what's interesting then about this odds ratio is that this stays the same no matter what the response category is used for j. Because notice here in this odds ratio, you don't see j at all. This corresponds to what we were talking about earlier when the proportional odds regression model was first introduced. And so because of that, we can even come up with the following interpretation, which will be a little bit easier because you don't need to specify the particular value of j. So we can say, for example, the odds of y being below a particular level are the exponential function evaluated at c times beta 1 times as large for a c unit increase in x. Now, here are some notes. If there's more than one explanatory variable, we always have to add then holding the other variables in the model constant. What happens if you have interactions? Suppose maybe you have a quadratic term. How do you find that odds ratio? How do you interpret it? Same as what we saw in chapter 2 in terms of the adjustments that need to be made. On tests or other graded items, I frequently will give questions about that to my students. As for inference methods, we can use WALD, we can use profile likelihood ratio. So let's take a look then at an example. We're going to go back to the weak kernels example that we've seen before. Now, each of these estimated odds ratios for our model are simply going to be the exponential function evaluated at c times the corresponding beta hat for that particular variable. Now, if you remember when we were first looking at the weak data example, we use a c equal 1 for the class variable, and then we use one standard deviation for the value of c corresponding to the other explanatory variables. And we're going to do exactly the same thing here. So here's then the corresponding code that we've actually used in the past. So remember the one standard deviation is 1.13 for density. Then to find then the corresponding odds ratio, I take all my c values, which are stored in my c dot value vector. I multiply it by the beta hats corresponding to the explanatory variables. How do you obtain them? Well, similar to what we did when we were working with the GLM function. We use $ coefficients. That does exist with the POLR function that's used to estimate this model. My results were stated in mod.fit.org, and notice the negative sign there. The reason why I needed to use the negative sign is remember that the POLR function estimates a slightly different version of the model that we are interested in. So just to make the correction, I put a negative out there. R correctly matches up the values in C.value with the values in mod.fit.org $ coefficients. I round everything to 2 decimal places, and here are my estimated odds ratios. If I were to invert the odds ratio, then this is what I get. So for example, let's focus on density there, 5.89. So the interpretation would be the estimated odds of a scab versus, so scab would be y is less than or equal to 1, versus a sprout or healthy, which would be y greater than 1. Response are 5.8 times as large for a 0.13 decrease, since I inverted that odds ratio, in density, holding the other variables constant. Now, what I could also do is I could take this scab, I could replace it with scab and sprout, and I could replace the sprout or healthy with only healthy. So this would be y is less than or equal to 2. This would be y greater than 2, and I get exactly the same interpretation. So because of that, then, I could instead phrase my interpretation like this. The estimated odds of kernel quality being below a particular level, where I don't state what that level is. The estimated odds of kernel quality being below a particular level are 5.89 times as large for a 0.13 decrease in the density level, holding the other variables constant. So I also give additional interpretations here corresponding to class and also for the weight variable. Make sure you read those. So what we see, and let's actually come back up here. So what we see here for our estimates is that for lower weights, lower density values, my estimated odds of having lower quality are higher than having higher quality. More on that shortly when we take a look at the confidence intervals. To do the confidence intervals, we can use profile likelihood ratio intervals. The confint function in R provides these intervals for us. So the mass function has a method function available that does the profile likelihood ratio intervals with respect to these kinds of models. Object equal mod.fit.org. I went 95% intervals. I put the results into conf.beta. Now, let me actually go ahead and go over to 10 to show you that. So what you see here are confidence intervals now for the eta parameters. So the actual confidence interval for the beta, what would be beta 2 for density, is negative 10.31 to negative 17. Actually, I should have reversed that. Negative 17.04 to negative 10.31. That would be the confidence interval for our beta for density. So then what I can do is I can form then the odds ratio confidence interval. So I take my C dot values times the negative of what's in conf.beta. Maybe I should have called this conf.eta. I never even thought of that, but so be very careful about that. So I take C dot value times the negative of conf.beta, because that's going to apply that negative sign correctly that we need to relate what POLR estimates versus how we define the model. I use the exponential function with this. I put it into an object called CI, and then I can go ahead and show my results. So if I were to invert then the corresponding confidence intervals, so I have a 0.13 decrease in density, my confidence interval is 3.87 to 9.36. Okay. Now notice, so an interpretation here is with 95% confidence, the odds of a scab instead of a sprout or healthy response. So scab again would be y is less than or equal to 1. Sprout or healthy would be y greater than 1. Response are 3.87 to 9.36 times as large when the density is decreased by 0.13, holding the other variables in the model constant. You could reword this instead and say, well, with 95% confidence, the odds of kernel quality being below a particular level are between 3.87 and 9.36 times as large when the density is decreased by 0.13, holding the other variables constant. So this additional interpretation comes about because, remember, J is not in our corresponding odds ratio equations. Now, if we come back up here, let's take a look at which of these odds ratio confidence intervals do not contain 1. So we have density, we have weight, and hardness is close but not quite. So what this says again is that we have sufficient evidence to indicate that density and weight have an effect on that corresponding health. I shouldn't say health, but the quality of the kernels. Where with hardness we have marginal evidence that it is important. Now, in terms of walled confidence intervals, confident.default actually doesn't work for these kinds of models, but we can use the EM means function. The EM means function can be quite useful in situations where you have a more complicated expression for your odds ratio, that as we've seen before. And so this is what I would use in this particular setting. Remember, as I said before, the MC profile package does not work here. So we're left with walled intervals as being, let's say, a more reasonable way to do these calculations. Okay, so to do the calculations in EM means, guess what? There's some quirkiness with this package within the corresponding function too. And once you understand what the correct argument values are, then you can get over the quirkiness here. But let's talk about it. So EM means object equal mod.fit.ord. And then in my specs argument, I say equal tilde, and I only put my explanatory variable of interest. Let's say I want to do odds ratio for density. This is different from what we saw with the multinom function, which made us to also put in the response variable too. Instead here, we only put in the one explanatory variable that we're interested in. And we can only do this for one explanatory variable at a time. Then for the at argument, now this does work as what we've seen like previously when we had what you could think of as an explanatory variable that has a continuous, which is continuous. And so I want to interpret density for a 1 standard deviation increase. Eventually we can do decrease as well in the value. And so for at, I have list density 1.25 plus 0.1 plus 0.13. That's like my C value. And then I have 1.25 again. I could have done something else other than 1.25. Again, as we've seen before, the key is I need to have that C value of 0.13 there. And then there's an argument that we've seen before called mode, but unfortunately the argument values are different from what we've seen. Now to eventually get to where we need to be, we need to actually say linear.predictor. In the end, from what we know what a linear predictor is, that maybe makes some sense because we are first going to do a confidence interval for beta, in other words, the log odds, and from that then we can find an odds ratio. So we do that, and then I use the confident function once again, and inside the confident function I decided to embed my code for contrast, object equal calc.s. method equal reverse pairwise. What that means is that I have these two levels here of density, and instead of comparing 1.38 to 1.25 in terms of the numerator and the denominator, now I'm going to flip them and have 1.25 to 1.38 so that I have a 1 standard deviation decrease in the density. On your own, you should think about the various other ways that you could have coded this so that maybe I didn't need to put reverse pairwise there. Maybe I could just put pairwise. Okay, then I need to say type equal response. 95% interval. Here is then my corresponding odds ratio. We've seen the 5.79 before. Here's my corresponding confidence interval. So I say 3.74 to 8.95 is my walled confidence interval for this particular setting. Okay, so some final comments then. Again, I've already said this. This is only for one explanatory variable at the time, so you would need to repeat the process for the other explanatory variables in your model. And I've basically covered these differences of using EM means with this model versus the multinomial regression model. Okay, so again, to interpret the effect that an explanatory variable has on the response when we have a proportional odds regression model, we go back to using odds ratios once again.